Okay, so now if we continue with synaptic properties, we said last time we can model this by looking at synaptic measure of the synapse here, of the bouton, is the number of vesicles available to release the neurotransmitters. And this is measured by mu. And we said that if you ignore this term, it's very elementary that if you solve this differential equation, you see between time t and t plus delta t, how much of the fraction of the vesicle have been eliminated, have been fused. You can say that if you have a spike, each time you have a spike, you reduce the number of vesicles available by this quantity. Let's say a certain number mu. R is 1. R of V, this is the conversion of voltage into spikes. But suppose you have RV equals 1. You are going to deplete by mu multiplied by u. So this is an exponential decay. And if there is nothing, it recovers to 1 with a rate tau r. This is what we discussed last time. And we said, now if you, again, to remind you what we did, we looked at the mean field model. So what is a mean field model? So you assume that you have many neurons connected, and they are sufficiently connected. The amount of connection is enough to see all of this as one large neuron, which behave differently than any other particular, because now it satisfies what is called the mean field equation. In that case, you can say that the voltage V is the average 1 over n of the voltage of each of them. All right. And so when you do this, you look at an equation for V, and we said that V decays, if nothing happens, it decays exponentially to 0, or it can be activated by self-connections with W of t, which is the synaptic weight, and there is mu, the depression, synaptic depression. And mu satisfies what I just explained to you a second ago, and you can add noise. Sigma is the variance of the noise, omega is the Brownian motion, mean 0, variance 1, and I of t could be an external stimulation. And what we saw last time is that if you ask what is the dynamic of this dynamical system, in other words, what is the behavior of the neuron, we say that it is characterized first by 3 points. The critical point where this is equal to 0. When you are interested in a dynamical system, you forget about this, you forget about this, and you start looking first at the point V and mu, such that V dot and mu dot equal 0, 0. So what we did last time, we did this calculation, and this led to what is called critical points. And we found 3 critical points. We had V equals 0 and mu equals 1. Why is that? Because if mu equals 1, this is 0. When V equals 0, V minus t plus, this means the positive part and t is a threshold. This, when V is 0, this is negative, so this is 0. So mu dot equals 0. The same, when V equals 0, this is 0, this is 0, and that's it. And so V dot, mu dot equals 0. So you have here a critical point. And there are 2 other critical points, V plus, mu plus, and V minus, mu minus, that are given by, I showed you last time, by solving a second order equation. And the result are those 3 points. You have V mu. When V equals 0, mu equals 1, you have this attractor here. You have a saddle point where trajectories goes in and goes out, and you have an attractor. And so now you can ask, what is the dynamic on this structure? The dynamic is the following. If you have, so first of all, you have an attractor, so everything is attracted to this point. Great. At this point, you know that it goes like this, and so a trajectory goes inside, converge, and a trajectory goes outside, and so then you have to, you know that the trajectory cannot intersect, that's the classical theory of dynamical system, and so you have something that should go like this, right? And what we discovered is that there is a limit cycle here. So trajectories can come here, they can cycle around the limit cycle from the time, negative time, that is when time is positive it goes in the opposite direction and ending here. But if you start inside the limit cycle, you converge to this point. And we say, what happens when you have noise? So what is the fate of a trajectory? If you start here, what happens? You go, and after some time you converge, and that's it, nothing happens. If you start here, you converge, and you reach this steady state, and that's it. To see interesting thing, you need the noise. And so, because of the noise, you can have the trajectories that escape. This is a classical theory of escape. You can follow my class. You can escape the bassin of attraction, move here, go into this attractor, and then escape from the attractor, and so on. And that's a typical simulation. Noise is able to create bistability between the two structures. One, inside the limit cycle. Second, outside. And here, because it's dimension 2, it's very easy. You can study the entire phenomena. And what we also discovered is that when you escape the limit cycle, you don't escape everywhere. You escape in a small region. So this is interesting because when you go around this point, so this point is called, it's a focus. A focus means that if you look at the matrix here of, you know, this is a point where the dynamics is 0, that is, there is no, it's a steady state. So you look at x dot equals mx, and you look at the matrix here, which is the Jacobian of the system. So it is an attractor, so if you diagonalize it, p minus tp, it's going to give you one eigenvalue and a second eigenvalue, lambda 1, lambda 2, and lambda 1 and lambda 2 are complex conjugated. It's a plus ib, and the one is a minus ib, and a is here negative, so it's an attractor, and b is this non-zero oscillation part. And what is interesting is that, so when you miss, so you go around, if there is no noise, you're going to rotate. Because of the noise, you can escape just this attraction towards 0, but if you miss the ensemble of points where you can escape, you have to go around until you escape. So you can escape with 0 rotation, 1, 2, 3, and so on. So you quantify the escape by the number of rotations. So we discussed this last time. And if you look at the dynamics, is you run your simulation, and what you see associated to this dynamical system, you look at the voltage, and you see that you can be in close to v equals 0. You have a population spike that leads to the dynamics where you are in a state which is depolarized. And in a depolarized state, you oscillate, which means that there is a frequency. If you look at the spectrogram, here you will see a frequency, a dominating frequency, which is characterized by omega. Until you go back to escape the attractor and converge to, you escape this limit cycle and go back to this point. That's what happened here. What you win by this analysis is that you don't know what is the depression of the system if you do experiments. But now you can look at mu, which gives you an information about the synaptic property. So if the model is correct, in replicating reality, you have access to a new parameter, which is the synaptic property of your well-connected ensemble of neurons, which is interesting. Okay? So this is an example of this up and down state. Yeah, go ahead.
Here on the simulation, do you put an input?
No input.
No input?
Just noise.
So this means that if the vesicles are full, then it will go to upstate.
What do you mean full?
I mean, you get like all the vesicles, the depression goes to one.
This is the depression here. So when you are, so you start here at 1. This comes from some depressed moment. Then when you're here, you go to the upstate where the neurons are firing. So if they are firing, the number of vesicles available will decrease. That's why you're here. Until you escape, where you recover. Okay? Okay, so let's continue. Now, there's something interesting here. Now I'll show you, I'm not going to do the calculation, I'm going to describe the calculation for you. So, there are 3 critical points we just discussed. 2 attractors, the one at the bottom, one inside the limit cycle, and the saddle point. If I look at what happened at the attractor inside the limit cycle, as we said, this point is a focus, and so you can calculate the Jacobian, which is the first derivative of the coordinates, with respect to all parameters. And you can calculate the eigenvalues. It's not very hard, right? It's you know, it's a way to diagonalize the matrix, it gives you the eigenvalue, and it gives you the imaginary part. And the imaginary part, what is very interesting, it depends on the parameters, which is u, which is a constant, but most important, it depends on J, the connectivity. In a very nonlinear manner that I'm not writing here. I think we wrote it somewhere. And so it means that in the frequency, what defines the frequency of oscillation is the combination of all these parameters, including the level of connectivity of the network. In other words, if you change the connectivity of a network, it should be reflected in the rate of oscillation that you see in this upstate. Which is interesting because you have something here to relate oscillation, which is a time series effect, to the property of your underlying connected network. And so at that time, we plotted this imaginary part. It was very nonlinear. And we look at the connectivity. And we could measure some of the oscillations. And we said, all right, if you have specific oscillations here, we went back to the level of connectivity. Now you can ask, you can say, all right, what are those numbers? What is the meaning of this number? 1837. So this is another challenge. It's to calibrate the parameter of the model to the data. This we didn't do, but we said that if there is a change in the value you can extract about this imaginary part, you can infer a change in the level of connectivity. Okay, so I think this is, and yeah, we went up to here. Those are data recorded from neurons in the auditory cortex, the barrel cortex. And at that time, what we did is said, all right, we looked here at the time of this upstate, and we segmented the signal. And we asked, what is the distribution of the time spent in the upstate? And so at that time, everybody was fitting a Gaussian or any kind of curve that looks close to the data, but we said, no, according to our theory, we should have this oscillation, and escaping from the attractor is quantified by the loop, because I showed to you that you can only escape in a small region. And that's why when we used our model, we could capture the peak and say the peak here, they have a meaning. It's not that they are isolated statistic that you need more statistics. No, there is something. You see, the goal of a model is beyond statistics, is to reveal something that is not obvious. And so we did that on two different types of recording, found that indeed the peaks here meant something, and this was what we did about 10 years ago. All right, so this is a summary. You have a dynamical system, you study it in the phase space, you can study the property in time of the two variables. This is something give you hidden information about what happened at the synapse, and there is a quantification of the peak. That is, if you look at a distribution like this and you try to fit it by a Poisson distribution, it's okay for some times, but you will not understand the peaks. The peaks, they have to come, they have to be studied separately through this analysis. And I showed to you how to apply this to data. Okay, now let's move on. This is one day we were called upon to ask, here is an experiment where you culture neurons, let's say an island of neurons, 34, let's say hundreds of neurons. So you see that they are forming recurrent connections. So far so good. And when they looked at the data, they found out that when a neuron is excited, it leads to an excitation of the ensemble, of the islands. And the excitation could last for seconds, which has nothing to do with the classical time scale of spike or depolarization. And so what was interesting, they started to quantify this from a physiological point of view. So once a neuron is activated, you see something that remains active, this is the depolarization, for seconds. And if you look at the calcium activity of each neuron, you see that they are all activated at the same time. So you activate one, and this, as a result, activate all of them. Okay, and the last piece of information that we had is that if you block synaptic activity, if you block the activity, if you stimulate one neuron, instead of having this response, you have nothing. Again, showing that this property has to do with synaptic properties. So one neuron or an ensemble of neurons sufficiently connected is not the same. Did you see the difference? Okay, so now the question was, where does that come from? Is this sufficient to use the synaptic property that we just discussed? I introduced to you depression and facilitation to explain this. Right? Because you can say, look, this is the right thing, that you can have synapse that will be activated by facilitation. So you accumulate calcium, leading to calcium, leading to the release across the neurons. And after some time, they release, and then they don't have any more. They don't have any more vesicles available, and that's why you get to the depression. All right. So then came another experiment exactly on this, and now you are going to tell me what you think. So this is the stimulation of one neuron. What we just discussed now, it activates all of them. You agree? And that's what we saw just in the previous slide. And then it comes back. Now suppose you activate after a few seconds. What do you see? You see that you don't have anymore the same response. But if you wait sufficiently long enough and you reactivate, you are back to the first response. And if you reactivate again at 5 seconds or few seconds of interval, you get a smaller response. So how do we? That's what we faced a couple of years ago, they asked, why is that? If the first one we said could be depression facilitation, if the model is correct, without changing the model, we should be able to get exact all of this. And that's a very constraint on the model. All right, so I'll show you how we answer this question. What we did is we said, so can we understand the data? What model do we need to use? And can we predict how the neuronal network behave when changing key parameters? Because maybe those are due to the fact that you have many connections, and if you have a different neural network, maybe the pattern that we have, that's showed to you, is going to be a little bit different. Actually, this is what you see here. You saw here the same, but for a different culture. So there's some variability. But it's reproducible more or less. You have the classical idea of having a less pronounced second spike is clear. Okay, so I explained to you, so this is now, if you go back to the full model where you model neuron by neuron, you have here the depression that we just discussed. This is when you have only one, suppose Q equals only to 1, you have the contribution of the network property. Here is the conversion of depolarization to spike. This is a noise. And we have two more parameters. Mu is a depression, so this we discussed, and we have facilitation. What is the facilitation variable? It should account for the fact that when you have a spike, calcium is going to be generated for some times, and then it will disappear. So it is generated at a certain level, it goes up to a certain maximum level and comes back. So this is expressed here. When there is nothing, it converges. This is an exponential y dot x minus y converge to x. So you are at a certain calcium concentration, which is x, and if you fire a lot, this term will become negligible, and y will converge to 1, which is another. It's normalized, right? It converges to a different point, and then you expect that once you send this, you have something that goes up and down. So that's what the facilitation is doing for you. This is empirical description of something that could be modeled in a more detailed way. This is what Roy is doing in the book to try to understand how calcium is generated. So we have three equations, and in the mean field model, if everybody is well connected, you have the three equations. One you already saw. This is what I showed you before. This is a depression, and then we had facilitation. So you have a dynamical system in dimension 3, plus noise, plus an input. So now how to connect the model to the experiments. That's the interesting part. Well, noise, I'm not sure we had much noise. We only had a stimulation at time 0, which was the pipette stimulation. That's the I of t here, which is going to be a delta Dirac at a moment of time with a certain amplitude. And the question is, if you simulate this, do you get what we observe experimentally? So that's what we did. The difficulty in all of this is to find the parameters. And that's how we spend months or years. I'd say months. So we have 1, 2, 3, 4, 5, 6, 7, 8, and maybe I forgot 10, 9. I think we have between 8 and 9 parameters. 8 and 9 parameters, you're in dimension 8 or 9. Exploring such parameter space is not easy. you need to start with some guess or to look in the literature what is known and what is not. Otherwise, you spend too much time. All right, so we knew some parameters, tau r, tau f, and the rest. X, we took it from also the literature. H, we use it from I think we fixed H, and we started to do the simulations. Actually, we did a lot of simulations until we found these parameters, until we understood that we could replicate this. And that was beautiful. That was beautiful. So what do you learn from this? Because you say, all right, you know, if models is just to reproduce nature, so what? Let's go to machine learning. You don't care about modeling. It will reproduce some of the reality, and you don't have to understand how to model. You just need to get the prediction. Okay. So this is what we got. But what we didn't know is, what we understood is by showing the facilitation and the depression. So this is the facilitation. You see at the beginning, to engage all of the neurons, you need this facilitation event that will create calcium, the first calcium peak. But what was interesting is that why this is smaller. Why? Because when you look at the depression variable, it takes a long time to go back to where it was. Thus, when you stimulate the second peak, you still have not enough vesicles. And thus the depressions is still active. That's why you get a smaller peak until it goes back to normal, where there is no depression, and then it repeats itself. So we were satisfied. We said, great, we have a model, and it tells us about some reality. And then they did an experiment where they change a little bit the concentration of calcium. And when they change the concentration of calcium, there was the same. The second peak was not reduced. This was again something that we had to work on, and we understood that this has to do with the variable X variable, which I explained to you, which is the variable in the facilitation. It changed the level of calcium, so such that now if you look at the facilitation and depression, you can see that you can have a facilitation, you have this facilitation, but the depression here was much faster. So that if you don't have this depression, or if you don't have this facilitation that is continuing, the second peak here will be almost the same as the first peak. So calcium channel prostatic terminal is diminished, decrease in facilitation. Depression dynamic is not affected. I don't understand something here. I have to go back to the name of the because I changed variable. So why is the facilitation? So why here is the facilitation? Okay, and the depression doesn't look right. I think this should be the depression because it takes time. Okay.
It's going to 0.95, so it's not really.
You're right. This is not very significant.
Yeah.
That's right. Okay, now I understand. Thanks, Philippe. Okay. So that's correct. So it's almost nothing. Okay, and then what we did is we varied the connectivity and look how the burst duration, so the period of time the burst is lasting, as a function of the connectivity. And what is interesting, we saw that there is, for example, there is another parameter here, I'm sorry, you don't see very well, is K, where we found out that there is an an interesting point here, because after this, you know, it was disappearing. And I know, yeah, I understand why I drew this one. This one is the one that we obtained from the data. So this is the way, the opportunity to calibrate, because if you say, now I have this from the data at this point, I know what's the connectivity I put the J was arbitrary, and then we ask our collaborator to count the number of synapses. So this is a way to relate, let's say, the average number of synapses that is present. We could not count where they were exactly, too many neurons, but we had this idea at that time. So this was a way to calibrate this J to an effective number of synapses. Okay, I think that's, yeah, okay, now I can spend a little bit of time to go into some math, which was not trivial, but I don't want to go into the calculation, it's a little bit tedious. But suppose I ask you, from this dynamical system, find the duration of the burst. Tell me how much it depends on the different parameters, J, H, X, kappa, L, TR. How would you do this? So it's complicated. So what we said at that time is that you start with H, you give a spike, it lasts some times, and then it decays. And I'm interested in evaluating this time, this duration. Can we estimate this duration? And so I'm going to explain to you how we did it. We said, fine, you have your delta stimulation, and I want to find the time such that this will reach a certain threshold, TR. I fix the threshold. So, of course, it will depend on TR, because if it goes exponentially, I can wait infinity to reach 0, I don't care. So, how much it takes to reach TR is, this will, if it starts at T steam equals 0, this will give me this duration. That's what we wanted to solve. And here we played a trick. We said that this is almost H. Almost H. So why don't we replace in this equation H of T, which could change, by just a constant? That was the trick. That was the trick as a first approximation. So you replace in here little h by capital H. Alright, now it becomes easy. It's not anymore a coupled system of equation. You have x, x, x dot, the rest is constant. So it's ordinary differential equation order 1. It's what you learn at school. So you can solve. It's like this, a plus b exponential something. Once you have solved this for x, x is a function of time. If it's a function of time, this is f of t, and now you can solve it for y. And y is just the method of variation of constants to get y of t. I get x of t, I get y of t, and then here, let's remember what, yeah, and it depends on the function f of t that you know what it is. It's a function that depends on x, as we said. And based on this, if you know x and y, if I know x of y, then you can go back here, because now that depends only on time, and you have a function of h that you can solve, and you get h. Although it was constant, now you want to put it back into the system to see what happened when it would vary. You have this expression, and now you can. So what we did is, the difficulty was to calculate this product x multiplied by y, where you have to, it's just arithmetic at this point. X is a function of t, y is a function of t which depend on f of t, which is, so it's going to be exponential of exponential. You have exponential of exponential. So at this point, okay, we can go and follow each calculation. I'm not sure this is interesting, but the method is interesting by itself. That's why I wanted to show you how we can do this calculation. And in the end, you can calculate, you calculate, and you get an expression for h of t, which depends on the exponential. It's not very interesting, but now we solve h of t equals threshold, which give you the tr, and then you have to invert this, and this gives us an estimation of the time to threshold, which is actually log of the threshold, which when you vary a little bit, the threshold doesn't change much. Okay, that was the solution, and what we were interested in again is how the threshold, how the time in this upstate, this bursting activity, depend on the connectivity. And then we had the formula, and that's what, of course you can say, look, if you change a little bit the threshold, it will affect this term. That's right. But at least here you see how it depends on the level of connectivity. And it shows that why now you can understand if you have too much connections, why TR, I mean, what is the meaning of these curves here? If you increase the level of connectivity, why there is a maximum? Because if there is not enough connectivity, you are going to use the facilitation, but it will not all neuron will participate, maybe only a small fraction. And more you have connectivity, and more you engage the network, which you arrive to here. But at some point, if you have too much connectivity, when you have a lot of depression, you have depression, it will suppress everybody at the same time, or more or less at the same time. And so the duration, because depression will be important, it's going to lead here to this maximum and this decrease. But instead of giving this interpretation, which you can accept or not, you just look at how this t depends on j, and this will give you the solution. Okay. Increasing the synaptic strength sublinear change in the bursting time. This is what I just explained to you. It goes first slowly, and then you go to the maximum. The neuronal network operates in a regime close to the optimal burst response. This was a surprise to see that the maximum where we were exactly at the maximum. Calcium regulate facilitation, reverberation bursting invariant by scaling. Okay, this I'm not going to discuss much. Okay, so to summarize, this dynamical system, 9 parameters, 6 were fixed by the literature. We had to look for 3 of them, and by trial and error, we found them. Okay, do you want to make a break, or do you want to continue? And we stop in 20 minutes. Maybe let's do this so that we stop in 20 minutes. Yeah. All right. This is a 3D representation of what I just showed to you. Depression, facilitation, mean voltage. You start from 0, you go to this tracker where you actually before this is oscillation, and by noise it can escape and go back. And what we found is that in this upstate, as I told you, there is this rotation attractor. You have some oscillations, and the oscillations is associated, can be measured, or can be characterized by a rhythm. And we said that the rhythm depends on the level of connectivity, because omega, as I showed you, depends on j. Okay. That's what we did. So, from the first paper, 2006, we did this analysis in 2014. Then what I showed you was published in 2016. And then we came back in 2020. It's not that long, but it's still 15 years of accumulation of ideas, and we understood. So if you look at what happened here, so you just look at the mean voltage as a function of time, you look at this rhythm, and to analyze this rhythm, you remember this was the first class, we looked at the power spectrum, the spectrogram, as a spectrum as a function of time. We saw that indeed there is this dominant frequency of oscillations, which means that there is a possible alpha theta rhythm when you are in this depolarized state. That comes just as a nature of the interaction between synapses and the neuronal networks. Okay, so how the next stage was to connect. So as you know, in the brain there are excitatory neuron and inhibitory neuron. So we have the inhibitory neuron here, excitatory neuron there. So the excitatory neuron can excite the inhibitory. You can stimulate here the inhibitory, and I will explain why and where we are converging with this. We're converging towards a model of anesthesia. Because we say what is anesthesia is you stimulate the inhibitory neuron. Right? You are going to activate the GABA. It's one way to go into anesthesia. So you stimulate here, and we wanted to see first of all if you have inhibitory neuron that can inhibit this excitatory. The excitatory, they can excite themselves, and they can excite the inhibitory. So we said first of all, what kind of dynamics can I expect from a coupled system where you have noise? So first of all, you have to connect. So you can connect and say, for example, they have all of them, they have depression, facilitation, and a voltage. Here I'm going to just show something simpler, and then I'll go back to this coupling using the full system in the next slides. So now I can look at the excitatory neuron, I can look at the inhibitory neurons, and look at the wave, the oscillation. And what do you see? You see that for some parameter that we tweak, I agree, but you see the effect that if you generate such neuronal network activity, I'll explain in a second how it is simulated, you get this property of having a peak in the alpha band in around 10 Hz that persists. And because they are coupled, you can see that it is reflected also in the inhibitory network, and when you sum the two, which is a measure of the total activity, you see that it gives something like this. So again, how do you do this? Excitatory neuron, they are excited, so you do a mean field model. This is one neuron activated, one inhibitory ensemble that is going to inhibit one excitatory ensemble. So here you have the depression. So I just wrote here the depression for the excitatory variable. So this is the amount of connectivity that you give here to excite itself. It is inhibited by with a certain level of connectivity. This is this JPI, and you can add noise. While the inhibitory neurons, they are inhibited by themselves, and they are activated with a certain depression corresponding only the Y is only in this E variable in the excitatory neuron. So they are activated by this excitatory neuron, and you have noise. And you have this depression, and this shows how the two are affecting each other. Okay, and then we said, let's go it's look a lot of equation, but you will see. We will go slowly, and you will understand it's not hard. After what I described to you with depression facilitation and what I show you with these two ensemble, we are going to go through this easily. But let's first look at how we model the cortex. We said the cortex and the thalamus, which is responsible, could be separated into three ensemble. One that would basically generate some kind of alpha rhythm, a rhythm that would be constant. It's not that I'm imposing. I will show you how we developed it. One can switch between up and down state. So this means that J alpha would be high enough so that this stays up so that you have a lot of connectivity. This should not be very well connected, so you can have transition between up and down state, which create the delta rhythm. And this, we should have here an inhibitory neurons ensemble. And now the difficulty is how you put the arrows. So this should be inhibiting this because they are inhibitory neuron. This should activate this one. This should inhibit this one. And this is they are excitators, so they should excite each other. And in addition, you have this with excite itself, inhibit itself. And when you give a drug, this should stimulate this. That is, you will have an input in only this NR.
How do you know that alpha doesn't excite on R? Because it's the only arrows that you didn't.
Alpha doesn't excite this?
Yes.
Yeah, because I think we made an hypothesis. Yeah, I think we tried and didn't give much. And at some point we removed this. So this is how we arrived to this.
And how much is in the cortex versus the thalamus? Like
How much?
The inhibitory are in the
Well, it's maybe François knows better because this would represent this reticular nuclei. You know, I don't know exactly where they are. They are in the thalamus, on the
shell
around the thalamus. Okay, so they are around. Okay, so now what do? Once you understand the arrows, positive, negative, you write for each of them the H, the depression, facilitation, the H, the depression, facilitation, the H, depression, facilitation. So you have 1, 2, and 3. And now you do the same as I did before. You have so there's something more here. I'm not going to discuss this for the moment. But you have the positivity when you go from, let's say, UD, it is activated by itself. It's going to be stimulated by alpha. This is this one, this connection, so it's a plus. And it's going to be inhibited by this one, which is this J, plus noise. And you can go over all of this. Once you understand how you do one, you just do what I showed to you before. So there's no point of going into the details, but now you have much more variables, and you can constrain this by what we showed to you for the previous model, and see what kind of result you get. So you simulate what I just showed to you. You can see that when you are in this upstate mode, you generate this effect. And if you stimulate with an electrode, you can force the inhibitory neuron to shut down everybody. This is what you see here. And see, for example, how when you stop the inhibition, you stop the drug. It's called an hypnotic, like propofol or whatever. Then it goes back to this activity. Okay, so now you can look at each network separately. I say I'm interested in network 1, network 2, network 3. We have 3 of them. And see how they respond. And not only I can see what happened for the voltage, but I can see the depression and facilitation, which is something that you gain because you don't see usually this. So what we did is we say, okay, now let's send, for example, a constant negative input, which is like you give a certain concentration of hypnotic. How this will affect the behavior. And so you see here that, so I don't remember if we put it somewhere here, but so you see the activity before, then you switch to some kind of this state where you have this rhythm, which is reminiscent of the rhythm that we observe. It's called the alpha waves. So we said that finally we can produce it and we can understand better how this has been produced. And you can look specifically, this is a magnification of this region, how you make a transition when you go at the beginning here, if you're at the center, and also, and what happened here when you exit from this region where you injected. This allows you basically to study your property of your dynamical system. Yeah, so again, this is an example. So you have an external stimulation. You remove any stimuli. So again, you have external stimulation. So suppose you impose here some kind of external eye, and then you stop them. What do you see? How the system is behaving. Right? This is again to mimic the fact that during anesthesia, you stop to have external input. And so the external input were like creating this kind of, looks like, the spiking properties, and then they are diminishing, they are vanishing here to reach the regime where you have this internal coupling that leads to this oscillation regime. Okay, and you can go on and on in terms of, if you look at the activity at the moment. So this is, so we played at this point to, for example, you give an input, and we said when you begin and when you end, what is the shift between the moment you stop and the moment you have your spiking here. So we quantify all of this. But what was interesting is, again, if you look at this pattern of activity, it looks like spindles. Very nice spindle type, and this is how we went to the first class or the second class, where we spent a lot of time just on this motif. What is the spindle and the fact that they could be generated by Ornstein-Uhlenbeck style processes, because they are just corresponding to the local oscillations near the attractor, while the entire activity to switch between the different regions, the different type of oscillations, has to do with the dynamics of the complex system. Okay, so in the last, I give you a lot of information today, a lot. I'm going to give 2 more slides, and then I think we should break, and this will be for next time. Now I'm going to announce the class of next week. Today, we haven't discussed much of astrocytes. And I explained to you that they could play a role, that you have these neurons, can feed back to the astrocytes. The question is how? And so we are going to finish with an experiment where you are going to change the way the astrocytic network is connected. So bear with me a second. You have one network and you have a second network, and I'm affecting this network. I'm preventing this network to communicate between itself. I'm preventing glial cells, astrocytes, to communicate between itself. How this will impact the neuronal network? You understand the question? found out that you can create conditions to generate epilepsy. Epilepsy is associated to this burst, 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 burst. This is in your neuron. You record in the neuron. Up to here, this is what a normal preparation should give. This activity. Now you mess up with the glial cells, and you still record on the voltage, and you see this. And again, it took us a couple of years to understand just this. Why, when you change the communication between the astrocytes, you get a different pattern of activity that should look like this when they are not affected. It means that the astrocyte does something and the network does something. Now we're talking about networks because we disconnected, we change, we suppress the gap junction that I showed you at the beginning. You remember the pipette story? Now I break this, and if you break this, you get this. Now the question is, what is happening? Okay, and so this is going to be the next class. I'm going to show you that we need to understand, to add something in the model, which is called after hyperpolarization, to understand this and to understand how when you change, when you affect the glial cells connectivity, which in some sense you affect what should happen inside the astrocytes, it reverberates, it has a consequence on the neuronal activity. And that's a way to understand how two networks communicate. You know, it's like, if you're interested, you can ask, is the subway in Paris interact much with the car network? The answer in principle is no, there's no interaction, because one lives on the top of each other and they're disconnected. However, if there is a strike in Paris and there is no more subway, suddenly there are much more cars, and it disrupts the car network. But you see, it's complex. We have to dissect, detail per detail, what is the mechanism. So next week, I'll explain to you how you can first of all segment this and go from, so this is another experiment where you have an epileptic pattern and how this is going to be broken. Instead of having a long type epilepsy motif, you get burst of epilepsy because you disrupted the glial network. How can this be? What is the interpretation for this? And what is the underlying phenomena, and where the model is used to say something. Okay, so I think I will stop here, and next week I will introduce for this a new phenomena which is called after hyperpolarization. Is the fact that if you have spike, after the last one, there is a period of time where the neurons, they go into a mode where nothing can happen to them. If you stimulate them, they are dead because they are what is called hyperpolarized. They don't react. And this takes time. And we will see next week that this is one of the key phenomena that will be regulated when you disrupt this neuron, these glial cells, that will play a fundamental role. Okay, so I think we should stop now. Again, the class is a lot, but I think it's important to get the ideas and to see there is in dynamical system, it's noisy dynamical system, it's how you do approximation, how you calculate, but more important, why you go in this direction, why this is important, why modeling matters, and how you connect models with parameters. I'm not talking about the 5 billions parameters or whatever number of parameters you have in neuronal networks of ChatGPT and the others. We're talking about very few. But it's already very interesting to see how much you can do with very few. And this very nonlinear dynamics, which is completely avoided mostly with this learning type EI models. Because the goal is different here. We want to understand how neurons work. I'm not trying to classify or use this. Maybe I should give a class about how artificial neural networks are constructed and how the weight, could be changed by plasticity. So you can see that it's very different. The goal is different, and it has diverged. And it's not that the modern AI represents the brain, because all of these phenomena are not there. All right. I'll see you next week.